Okay, now we're going to look at the integrated rate law. So what we're doing here is we using some calculus to integrate the rate equations that we've been looking at. Now, I don't expect that you've had calculus and that you know how to do this, but I do expect that you know how to use the resulting equations that come out of this. Okay, and so why bother? Well, the why bother is that this helps us to, if we can use the information, we can look at time and concentration data and determine what reaction order we have. So we might not start with rate data. We might only have time and concentration data. And we can use this information to help us look at what happens as concentration changes on time and what effect does time have on concentration, and answer more questions, which is what it's all about, right? Okay, so take my word for it that if you use calculus and you integrate the rate law for a first order process, right? So here is a reactant, double the reactant, the rate doubles. If you know it's a first order process, what we know is the natural log of the concentration of that reactant at some given time over the concentration initially at the start of the reaction is equal to the negative of the rate constant times time. Okay? A0 is the initial concentration, AT is after some time that's defined. If we manipulate the equation, you get log of AT over A0 equals minus KT, and you keep rearranging it. You end up with a format that should look familiar to you, and that format would be what we have here, log of AT equals negative KT plus log of A0. And that is the equation for a line. Log of AT would be your Y, M would be your negative K, X is your T, and B is the log of A. Okay? So if we were to plot the log of some concentration data we were given, right, at a certain time, and we knew what the initial concentration was, we could determine how long it would take to do that. Or we could determine, given what the time is, how much of the product we should get. But most importantly is if we plot the log of the concentration, we have concentration data, versus time, this is my Y, right? This is my X, and it's a straight line that goes through the origin, it's actually going to go this way, then it is first order. This is how I can determine that it's first order reaction. Okay? And even neater than that is I can determine what my rate constant is, because the rate constant is going to be the slope, right? Y over X, or the log of A, the natural log of the concentration of A at a certain time, over time. Okay? Alright, so let's take a look at how we use this. So here's an equation that's just the same thing we just looked at. So if we have a reaction that's first order, a plot of log of A, like we just said, log of A versus time will give us a straight line. And the slope will be the negative of the K. And remember, the rate constant is always going to be a positive number. Okay? So let's say I have this methyl isonitrile, and it changes to acetonitrile. Same stuff in it, it's just rearranging. Okay? So let's take a look at this. And if I plot time versus pressure, now this is a gas, and I'm plotting pressure, I get a curve. I do not get a straight line. Now, why are they plotting pressure? Well, as it turns out, you know that the number of particles is directly proportional to pressure for a gas, right? We know that 1 mole of any gas occupies 22.4 liters. right? So we can use, when we're talking about gases, we can use pressure instead of molarity, right? Instead of the concentration and molarity. Okay, so it's just another way to identify how far the reaction has gone. Okay. So what we know is, it turns out if I were to plot time, let me see, time and some indication of how much stuff has reacted, like concentration or pressure, and I get a straight line, then that tells me my reaction is zero order. So concentration versus time is linear. It's a zero order reaction. Okay? But if it's a first order process, like this one is, this will not be curved, time versus concentration or pressure, but the log of the pressure or the concentration or whatever it is that we're using as an indicator of how much stuff is reacted, that will be a straight line. Okay? So if we plot the log of the pressure or the log of the concentration as a function of time, and we get a straight line, that tells us that our reaction is first order. Okay.
Hello?
And if we determine the slope of that line, okay, we can take change in y over change in x at any 2 points. We determined what the rate constant is, right? It's the negative of the slope. The slope is negative, so the rate constant is positive, and I can find the rate constant. So let's take a look at one. If we have a reaction where 2A leads to B, and it's first order with a rate constant of 2.8 times 10 to the minus 2 per second at 80 C, how long will it take for A to decrease from 0.88 to 0.14? Okay, so let's take a look at that equation we were looking at. What we know is the log of some concentration minus the initial is equal to minus the rate constant times time, right? And what we know, this is just rearranging it to get K positive. A0, the initial concentration, it tells us here is 0.88 in the problem, right? Right here. The new concentration that we're talking about, whoops, is 0.14 molar, okay? We're trying to find time. So if we rearrange this equation, we just put the, divide both sides by K, what we get is a log of the initial concentration minus a log of the concentration that we're talking about over K gives us the time. I can, if I have, am I subtracting the log of one thing minus a log of the other, I can rewrite that as the log of the first over the log of the second. And you'll see why that's important in a second. Okay. So if I take the log of the 0.88 molar over the 0.14 molar and divide it by K, the molars will cancel and I get 66 seconds. Okay? Now, one of the things that we can use this for is to determine what is going on with half-life. So let's just take a look at this again. So if we are looking for half-life, that half-life is, what we're talking about is how much time does it take for what I started as an initial quantity to be only half left, right? Half of it's gone? Okay. So when I'm talking about half-life, if I start with a reactant and it's got some concentration and I'm representing particles in a given amount of volume or molarity, and every one half-life takes half those particles and they go away, right? Another half-life and half of what was there goes away, and another half-life and half what was there goes away, right? So that's what we're talking about when we're talking about half-life. So half-life is defined as the time required for one half of the reactant to react. Okay? Okay, so what we're talking about there is this concentration that we're interested in is the initial concentration divided by 2. So like we said, if I'm taking the initial concentration and taking the log of that minus the log of the new concentration, I can put them over each other. And you can see what happens when you do that. The initial concentrations cancel. And I end up with the log of 2. Isn't that nice? Because the nice thing is that this is always the same number. So if we have a first order reaction, okay, this only applies to first order reactions, and we want to know what the half-life is, or we know the half-life and we want to know the rate constant, it's going to be 0.693 divided by K. Okay, always. So the half-life does not even depend at all on the initial concentration. It's not in the final equation. So for a first order process, this is only for a first order process, my half-life is 0.693 divided by the rate constant. Alright, so let's apply this. What is the half-life of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4 per second? That's what this is. Okay, so if I plug that into the equation, I get half-life, the time at 1/2 is log of 2 over K, which is 0.693 over the rate constant, and if I divide these, now this S minus 1, once I divide, is going to end up on the numerator, right? So it's going to be 1200 seconds, which I could convert to 20 minutes. Okay? And we know this is a first order reaction because of the units. We would only get these units for a rate constant S to the minus 1 if it were first order. Alright, so let's take a look at what happens with second order processes. If we do the calculus and integrate the rate law, what we get is that 1 over the concentration at a specific time equals KT plus 1 over the initial concentration. And this equation also is in the form of y equals mx plus b. And again, what we have here is if we plot on the x-axis time, on the y-axis 1 over a, concentration data per time, and we get a straight line, okay, we get a straight line. The slope of that line is going to be K, and we know that it is the second order for that reactant. Okay, so here we have some data. We have time, we have concentration of NO2 with that time. And if we take that data and we take the log of NO2, what we see is that the time versus log plot is not straight. It's a curve. So this is not first order. Okay? If I take that same NO2 concentration data and make a new calculation for 1 over the concentration, I get my straight line, and it's actually positive slope. I get a straight line. Okay? So the fact that the plot of time and 1 over the concentration gives me a straight line tells me that this is a second order process. Okay. Okay, just like we did with the first order reaction, we can change the concentration at a specific time when we're doing half-lives to we want a half of a initial concentration. And what that gives us down here is the equation that we want. Time, half-life, is 1 over K times the concentration. Alright. So in this case, we want to determine the reaction order from the integrated rate law. Okay? So what I'm going to show you how to use your graphing calculator to take the reaction data, time and concentration of this reactant, and determine whether it is 0th, first, or second order graphically. Okay, so let's turn on our calculator. Now the first thing you want to do, you can clear this, is you want to make sure your diagnostics are on. So I'm going to go to second catalog, second 0, which gives me the catalog, and I'm going to go down to diagnostics, and I want to select not diagnostics off but diagnostics on. There's two options here. I want to select diagnostics on and hit enter until it shows that it's done. Alright, I clear that. Now I want to go in and create my data, and I'm going to use the stat button to do that. And it's going to hit enter, which is defaults to 1, which is edit. Okay. When I go in there, I have a bunch of data, so rather than clearing it column by column, I'm going to do the big sweep, which is the clear all list, and I do that by hitting second memory, and then I want option 4 for clear all list, hit enter, and it should be done. Alright, so now I go back into stat, and I hit enter for edit, and my table is empty. I want to make sure I go over here all the way to L1, as far to the left as I can go. It's really important when you do this that you put your time in the first column. And sometimes you will get a data table that does not have it in the first column. Could be an AP test, could be one of my tests. So you need to make sure that your time always goes into L1. Okay? So I'm just going to go ahead and enter data, and you do the same. 0, 50, and if I'm going too fast, you can just pause until you catch up. If you missed something I said, you can go back and rewind. Okay, I'm going to keep entering data. 0.01. You should be doing this along with me. This should be my last data point. And I want to take a quick look at my data and look like it was all entered correctly. Okay, so if I take this data, this is time, this is concentration, and I were to plot this, and I got a straight line, that would tell me that the reaction order, is 0th order relative to NO2. Okay, so if time and concentration gives you a straight line, then you have a 0th order reaction relative to that reactant. Okay, so I want to compare that potential line to what it would be if it should be first order, which would be I want to plot time versus the log of the concentration. So in order to make this a calculated column, I have to go all the way up to the top above the line, and I want in L3 to put the log of the concentration. So I'm going to hit log of L2, which is my concentration data. So I hit second L2, close my parentheses, and hit enter. And here it's calculated my log. So if I plot this L1, which is time, versus the log of the concentration, and I get a straight line, that means I have a first order reaction relative to NO2. But I have one more thing to enter, because I want to compare that to the one over the concentration plotted versus time, because if that's the best line, that would tell me I have a second order reaction. Okay, so I'm going to go up to L4 at the very top, and I'm going to plot 1 divided by the concentration, which is second L2. Hit enter. And that should be the end of entering my data, doing my calculations. Now I want to, before I do my linear regression, which will tell me which line is best, I want to go into my statistics plot, and I do that by hitting second Y, so second Y equals, and I want to make sure that number 1, plot 1, is on. So I make sure my darkened area is on 1, and I hit enter, and it's on. I want to make sure I have the scatter plot here. I'm plotting L1, which is my time, versus L2, which is my concentration, and I hit enter. Okay, so that's all set. Now I want to hit stat, go back into where my data is, and I want to, instead of editing, I want to go over in calc. So hit calc, and I want to do a linear regression, number 4. Okay, so my x is L1, my y is L2, so I'm going to hit enter until it goes ahead and does the calculation for me. Okay, and this is what we're looking for. So the generic equation for a line is y equals ax plus b. Here a means the slope, so I got my slope, I got my b, which is my y-intercept. Key thing I'm looking for here is my r, which is my correlation coefficient. And the closer this number is to -1 or +1, the better the straight line. Okay? -1 if it's a negative slope, +1 if it's a positive slope. So what I want to do is record that for time versus concentration, my R is 0.9630. Let's go out at least 4 or 5 decimal places and record this, because this looks pretty good, but you will be surprised. You should be able to get R's that are even closer than that, to -1 or 1. So I want to record 0.9630 for concentration versus time. Now I want to now look at how that compares to plotting time versus the log of the concentration. And to do that, rather than re-entering all the linear regression stuff, I'm just going to pull up that, what I just did, and I'll do that by hitting second enter, which brings up my last entry. I did linear regression of ax plus b, and all I want to do is change L2 to L3, because that's where my log data is. So I hit second L3, hit enter, and I get an even better R, minus 0.99117. Okay, so I want to record that. This is my my correlation coefficient. Should I have a first order reaction plotting log of concentration versus time. So record this for the log of the concentration, 0.9912, let's say. Okay. Still need to look at what 1 over x, or 1 over the concentration, is doing versus time to see if that's even better. So I do that, pull it back up, second enter, brings up that entry. I want to change L3 to L4, which is where I have my 1 over my concentration. I hit second L4, and I hit enter, and look at that R, 0.99999, the best R. And what that tells me is this is the best line, and therefore, because it's 1 over the concentration versus time that gave me the best R, that this is a second order reaction. Okay. What's really cool is not only does it tell me it's second order, but it also tells me the slope. In this case, generic equation, A is the slope, and my slope is 0.543. And what does the slope tell us? If you remember, the slope tells us the rate constant. So I know this is second order, and I know what K is. Okay. Alright, so here, just to summarize, this is the data that should be in my calculator. If you did it some other way, you'd have it some other way. You're not going to have a computer available for you on the AP test, so you need to know how to do this on your graphing calculator. So we have time, my initial concentration data. All this was given to me in my original problem. I calculated the log of the concentration. I calculated 1 over the concentration. And the plot that gives me the best linear regression is this versus time, which means this is second order. If this versus this was best, this would be 0th order. If this versus this was best, that'd be first order. If this versus this was best, it would give me second order. So I have a second order reaction, and I know my slope, 0.543. Okay, and there we go.